Here's the reflectance curve for the blue-green ink. And here's the reflectance curve for the yellow. Obviously, we can see at a glance where in the spectrum we are going to come out. Green. And from the curves for the cyan and the yellow, we can compute the curve for the green, which will result from the two. Arriving at this third color as a result of overlapping or mixing the other two, as in color printing, is called subtractive mixing, for the simple reason that the second color, the cyan, cannot add anything to the yellow color under it, but can only subtract or absorb rays from the beam of light, in this case, the red and yellow rays. Thus, in color printing, 2, 3, and 4 colors are put on top of one another to get reproductions of an original painting or color photograph. Generally, though, the pigments are mixed beforehand, as in the original painting, then applied directly to a surface. Nevertheless, if the pigments are transparent, the color of the mixture can be accurately predicted by the reflectance curves of the colors to be mixed, for when light strikes the pigments, it follows the same rules as it did with the two inks we just saw. The processes of absorption, transmission, and reflectance are carried on just as with the dry inks, and the green we get can be predicted with just as much accuracy. Without this knowledge, this ability to know exactly how to determine and how to arrive at a desired color, not once, but thousands and thousands of times over, without this knowledge, virtually everything we have about us, from our clothes to our food packages, would look strange indeed. In fact, it becomes increasingly obvious the more we learn about the mysteries of color that modern production methods must lean heavily on the scientific control of pigments, dyes, and inks. So far, we have only considered subtractive color mixture, that is, where certain colors are filtered out, leaving others. What we are going to see now, however, is something else again, additive color mixture. Here is a pattern composed of alternating blue and yellow squares. But seen at a distance, where the eye can no longer distinguish the individual squares, we find that the two colors blend or mix. They blend in the eye, however, and not into the green we would expect by mixing two paints of these colors, but rather into a light gray. This too can be predicted by taking an average of the reflectance curves for the two colors. The curve we get from this average of the other two curves indicates a gray because of its flatness, meaning, as we can see, that it is neither high nor low at any particular wavelength, but is about the same for all. Here is another way of demonstrating additive color mixture, the Maxwell disc. The colors are rotated until again the eye can no longer distinguish them separately and sees only their mixture, which turns out to be the same gray as with the squares of blue and yellow. In general, artists use the subtractive method by mixing their colors before applying them to a surface. But there is one school of painting which utilizes additive mixture. The French impressionist Seurat was the first modern painter to make use of the technique of pointillism, which is nothing more than the laying on of small, individual dots of paint, which when juxtaposed in the mass, blend together in exactly the same manner as the blue and yellow squares did. But in this case, their colors were selected to produce an extremely lifelike effect. And a far cry from the 19th century French painting, it is interesting to note that today, the most up-to-date commercial application of additive mixture occurs in the most modern art form, color television, where the same principles hold. When we saw the yellow and blue squares a moment ago, we thought they would result in green. But by additive mixture, it turned out to be gray. And here, on color television, we find that it is red and green, which add up to being yellow. Now, as the scene changes on the television screen, let's see what new color red, blue, and green will give us. White, of all things. Now for a further complication. Let us suppose this object were to be televised. First, let us see the curve for this particular color. Very well. Now, here is the same object as it would appear when color televised. It looks to the eye to be the same as before, yet look at its curve now. Strangely enough, although the colors of the object appear to be the same when seen with the naked eye as when seen on color television, the curves for each are quite different. The explanation? It comes down to this: the human eye and how it sees. Another whole new field, and one we haven't time even to begin exploring in this film. We have found, however, that color is not an intrinsic property of physical objects, but depends to an equal or greater extent on different kinds of light and on the nature of the human eye. We have seen something of the behavior of color and light. Refraction, reflection, transparency, opacity, subtractive mixture, additive mixture. And we know this is a field for scientists and technicians, the people who have learned to control and manufacture coatings and coloring agents, printing inks, varnishes, lacquers, dyes, finishes, and textile colorings, to help beautify everything around us, wherever the eye falls, and to make that beauty permanent.